Today, we will try to implement a heap. And a heap is also called a priority queue. It's not a queue like a simple linked list. What it matters here, it's the priority. So it's like a priority list, priority queue, but priority is the main word here, okay? So don't focus on queue, because you'll see the implementation is not a simple linked list, okay? So let's add, where is the Solution Explorer? Okay, so let's add a file, new item, not C++ file, okay. And what we want here, it's obviously we need something with priorities. So when you talk about a priority queue, as the keyword is priority, it means you need to define it. What's priority? How you measure it? So if you have a structure that you need to process and store in a priority queue, this is the first thing that you need to decide. And this is the equivalent of talking about hash tables. And you need to identify what's the unique value that you associate with an article that you want to store in that dictionary. So remember, a hash table, it's a dictionary. So it will always use a key, a unique value associated to anything that you store there. So when we talk about the priority queue, the ID is not so important, but the priority. How do you measure it? Okay. And we were talking about messages with some priority. Okay, so let's go for this simple structure. Okay, so I need malloc. I need a standard input output. And yeah, I think that's all. And let's define the structure. So let's say these are Meteo messages, and here we have like you have the scale, the importance scale based on colors. Okay, alerts, Meteo alerts. Yeah, it's even better. Based on color. So you have, let's say, yellow, red alerts, which generally are associated with a high degree of risk. Okay, so here we want to process Meteo alerts based on their priority. And in order to define that, let's define the alert itself. So once again, I will go for a message, a fixed size message of 100 chars, because this is not important now. And what I need is this, the priority. Okay, so the priority will vary with different degrees. And what we want is to always process the Meteo alerts with the highest priority before going to the others. Okay, because maybe it's not maybe, it's sure that they are more important than the others. So we need to process them as fast as possible. Now, if you want to do this with an array, you can do it. So in the end, you can do anything with an array. But the problem here is that each time you want to get the new message, the new Meteo alert, you need to search for the one with the maximum priority. So we know that the sequential search in an array, it has the complexity n, because if you have n elements, sometimes the maximum, the value that you are searching for, could be the last one. So the complexity of the sequential search on an array is n. Okay, let's try with a list. So if I go for a list, a simple linked list or a double linked list, the problem and the solution are the same. Once again, complexity n. Maybe it's even more slower because, you know, you need to traverse the list going from different addresses to other addresses. So in this case, I will choose the array. It's faster. Okay, let's see if the hash table will help us. Now, the hash table will not help us because the hash table needs a key. So if you want to use the priority as the key, yes, you will find that Meteo alert, but the problem is that if you have multiple alerts, multiple messages with the same key, with the same priority, you can store only one. either the first one or the last one. In our previous examples, each time we updated the value associated with that key. So you have a hash table with meta alerts, you store them by their priority. If you get 100 meta alerts with the highest priority, let's say 100, you will always have in the hash table the last one. So you lose all the other 99. So it's not okay. So it's obvious that we need a dedicated structure, which will focus only on this to deliver the best solution for this case. So if I go back to the array, where I should have always the maximum priority in order to get it as fast as possible.
First element.
First element. So you may say, let's do that with an array. So each time you want to get the maximum priority alert, I will guarantee you is the first one. Okay, so you will have what? Complexity 1 of getting that message, which is perfect. What's the drawback? The drawback is that in order to make sure that every time you get a meta alert, the highest priority will be the first one, you need to do a lot of work. Because, okay, you may say for inserting it's simple. Each time you get a new meta alert, you need to check its priority against the first one. So if it's higher, you put the meta alert here and you move the previous first element to the end. And now you may say, hey, I have a solution for that. Now, what will be the thing that you need to do when you get that value from the first element? You need to search for the next maximum. So you see, you will lose a lot of time getting the next maximum in line. And once again, you can move to the end. So it's not feasible. We need something which is even faster than this. But the idea remains. This will be the goal, to have a data structure that will always guarantee us that the first one is the one that we want. So we will get it as fast as possible. So the idea, it's a good one. But a simple array has a problem with how it can handle that. Okay, so this is the reason why they invented priority queues or heaps. And you know from the course that a heap is actually a tree. Okay, so just a simple reminder to everyone, in order to understand the code that we will write, because the code is quite simple, but in order to understand why we do that. Okay, so yeah, let's try. I try to switch to whiteboard, something better than paint. What I want to show you is a quick reminder. Yes, now I have it. So I have the Microsoft whiteboard. Let's.
We can only see visuals.
Yeah. Accept. Okay. Yeah. Okay. Welcome. Get started. Okay. Next. Okay, let's go. Okay, so a heap is actually a complete binary tree. So what's a complete binary tree? A complete binary tree, it's something that looks like this. So what's a binary tree?
It's a tree that only has two children, like a node can only have two children.
Yeah, so this is a binary tree, okay? And what's a, let's say, complete binary tree? It's a binary tree in which the only level which is not complete, which may miss some values, is the last one. So if you get these values, let's try to, let's say 1, 10, 30, 7, and 9. If you want to build a complete binary tree and get these values one by one, the tree will look like this. The first value that you will get will be 1. So here you will have the root node of the tree 1. Now, the second value that you will get is 10. So you will always check to see if you have available spaces on the current level, but this is not the case. This is the root, it's already full. So now you move to the next level downwards. So we will always draw a tree in reverse order. The root will be upwards and the tree will grow downwards. And we will check the current, let's say, siblings or child nodes of this root node. So 10 will go here, okay? Because the next level is this one here, the second. This was the, let's say, the first level. So now we move to the next level and we fill up the next level from left to right. Okay, this is the natural order for us. We read and write from left to right. So this is 10. Now 30 will go here. Okay, it's the next available space on this line. Now 7, the second row, it's already full. So we need to move downwards. So 7 will go here. Okay, and now 9 will go here. Okay, so, and the story will go on forever. Like when you fill up this row, you move to the next level, to the next row downwards, and you guide the idea. So this is
basically a binary tree is where left side is always greater than the right side.
No, that's
less than the right side.
Yes, but that's not just a binary tree. It's a binary search tree.
Okay.
Now, any tree that has at maximum 2 child nodes or 2 siblings. So in any tree that each node may have 1 or 2 or 0 siblings, it's just a binary tree.
Okay.
So the binary property means only this. Each node may have 0, 1, or 2 siblings, and that's it. And the fact that you have relations between values in these nodes, like this value should always be less than this one, or this value should always be greater than this one, for example, this is an additional property, which in the end will make a binary tree to be a search binary tree.
So it makes it easier to be searchable.
Yeah, but you see, it's a particular case of a binary tree. So what it means, not all binary trees are search binary trees. You got the idea?
Yeah, I got the idea.
Okay, now this is a binary tree. And this is not just a binary tree, it's a complete binary tree, because you see, we have a special order when we insert. You see, always we fill the gaps, we fill the current row, and after that we move to the next one. Now, if you ask me to draw a normal binary tree, just a common binary tree, I may draw it like this. Okay, and after that I can put 7 here and 9 here. And if you ask me why I did this, I will just give you a simple answer, a personal answer. This I don't know, I imagine this tree. Okay, in my mind, this is the way the tree should look for those values. Now, if you try to draw it, you may get to a different representation, but this is just a normal binary tree. Okay, because you see, you have only this property. Each node may have 0, like this one, and this is called the leaf node. So if you have a node that has 0 siblings, that's a leaf node or a terminal node. Okay, so this is a normal binary tree. This is a complete binary tree, and next week we will go to search by binary trees, and there we have this relation between values. Okay. So a heap, it's a complete binary tree. Okay, so how that will help us having here the maximum value. Now, it's obviously that you will have here the maximum value if the order of the values here will start with the maximum. But otherwise, for example, if here we add 1000, and let's say these are priorities, it's obviously that 1000 will go here. So it's not the first one. So how can we make from a complete binary tree to be a heap? Okay, because we established the main idea of a heap was to give us as fast as possible the message or the value with the highest priority or with the highest value. which we established that it should be this. So how this value will get from this normal location accordingly with the rules of a complete binary tree here. And it's obviously that we need today to do something more than a complete, let's say a normal complete binary tree. And what we will do is to check the values, okay, by comparing them. So let's rephrase. A heap is a complete binary tree, and from this we get what? We get the insertion rule. When you hear complete binary tree, you will always know that if you get here another value like 5, you don't need to ask where 5 will go. Now, if I go back to this strange binary tree, yes, this is a valid question. When do you want to store 5? I don't know, here, here, or here. Depends. But in a complete binary tree, 5 will always go in the only place that it can go in a complete binary tree, which is here. Okay, the next available location on the current row. And if this row is filled, so let's say you get another value like 7, this will go here. So you have another 7 here. Okay, so when you hear about a complete binary tree and someone will ask you to insert something there, you don't need to ask where. You already know. This is the property of a complete binary tree. You will always know where to insert a new element by just following this simple rule. Fill up the current row, move to the next one, fill the next row from left to right. Okay, so this is the property of a complete binary tree. Now, how can we make from a complete binary tree a heap? So once again, let's say here you get 2000. Okay, so it's normally this will go here, 2000. Okay, so it will go here. This is the next location. So how can I move this here? And if I achieve that, we have a heap. So in order to do this, we will always, after inserting, we will always compare 2000, the last value, with its parent value. So if this value is greater than its parent value, we do what? We do a switch. Okay, and after we do the switch, so 2000 goes here, and now you have 7 here. And after you do the switch, you continue asking yourself this: hey, how are you compared to your parent? Are you greater or lesser? So if 2000 is greater than 10, you do another switch. So now you have 10 here and 2000 here. Okay, and you continue asking this. You continue comparing the current node, the current location at which you are, with its parent value. So once again, you compare them. 2000, it's obviously greater than 1. So now you have 2000 here and 1 is here. Okay, so a heap, it's a data structure. It's a complete binary tree in which each time when you insert a value, you insert the value as in a normal complete binary tree, and after that you compare this value with its parent, and you interchange them until you reach the root. Here you don't have any parents, so you stop, or you find yourself in a, let's say, scenario where this node is less than, it has a value less than its parent. So you don't need to do the switch, you stop. Okay, so this is the insertion. So at this point, the heap will deliver what it's promising to us. You have here in the root node of this tree, the value, the maximum value, if this is a maximum priority heap. So what I will do, I will get this value in the fastest way possible. And when you get something out of a structure, this generally means delete. So you get it and you remove it, okay? You don't leave the value there. So what will happen if you have a heap like this one and you need to extract the maximum value, because this is the idea, okay, to extract it. So if I draw, let's say, no, not this one, a new page, what's the add image? How do I clear this one? Yeah, let's see. Add image, paste that text, more what? Clear canvas. Okay, so if I start with the previous heap, so let's draw it again. Okay, so here you had 2000. Okay, now here maybe we got 50, whatever. So I will just draw some values, 30, and maybe here we have a 7, and here we have 25. So we have this heap. It's a complete binary tree. Okay, we check the properties. What will happen if you need to remove this one? So this is processed, gets out. Obviously, you can't leave that space unoccupied, because the next time you insert, maybe you get here 5,000, you compare it with 30, and you do the switch here, and after that you compare to 5,000 with what's here. It's empty, it's not zero, it's nothing. So when you delete something from a heap, which means you got the message with the highest priority, or the value with the highest priority, you need to put something here in place. So now you may think to do this. Let's do the maximum between the two siblings. Okay, choose the maximum and put the maximum here. And now you have an empty location here. And you do again the maximum and the maximum. Okay, so in this way you will work a lot in order to achieve that and to get the maximum again here. Okay, so in this way you once again bring back the maximum here. But what's the problem? The problem is that if you always compare this with the maximum, okay, you may reach, for example, a location here by going downwards. So at one moment the maximum will be on this row, and you will, let's say, leave an empty space there. Okay, so the binary tree will not be a complete one because you will have a gap in one row, for example. Okay, so in this case, what will be the easiest way to replace 2000 with a value from the binary complete tree? So what was the solution? You discussed about this, right?
Isn't it easier to compare it first to 50 or 30 and see which is the greater value, and we put the greater value, the greater value in place of 2000?
Yeah, but you see, let's do this. And what I want to do is, let's suppose here you have 27.
Okay.
So what's the maximum between 50 and 30? 50, right? It's obviously. So this goes here. And now you have an empty space here. And once again, you need to get the maximum between the two siblings, right?
Yes, of course.
Which is 27 and 25. Which is the maximum? 27, right?
27, yeah.
So if you remove 27 from here and put it here, is this a complete binary tree?
Not really.
No. So you just lost the property, because the next value that you will get here will go here, right? How do you find these gaps? So this is not a solution, because it may lead to this case where you break the complete binary tree.
Okay.
So
you replace the root with the last inserted element in the heap.
Exactly.
And then you delete the last element.
Yes. So let's do this. I will draw again this. So 2000 was out. Here you have 50. So in a complete binary tree, which is the node that you can always delete without worrying that you will lose the complete binary tree? Which is the node, just ignore its value, which is the node that you can always delete and be sure that after that the tree is still a complete binary tree? So if you have this image, which is the node that you can always delete? Yeah,
the last one.
The last one. And which is the last node in a complete binary tree?
25 in our case.
Exactly. So you will always look on the last level, 27, 25, and pick the last from left to right, the last node that has a value. So in order to avoid this case, this is half true, the solution here. But you see, it can lead to these strange situations when you have gaps on a row and then you lose the complete binary tree. It's not a complete binary tree anymore. So you just broken it. So it's obviously that by removing 2000 from here, we need to put here a value from the tree itself. And in that way, you need to delete a node elsewhere. And the safest node that you can delete is this always. Like your colleague said, the last one. So what I will do, I will get the last node value, put it here, delete it, and now it's safe. I can always delete this one, the last node can always be deleted. And after that, you still have a binary complete tree. But now we have a problem with the heap. Who guarantees us that this is the next maximum value in the heap? No one. So after you do this, you need to be sure that you remain here with a maximum value. So what do? Is the solution from this part. You compare 25 with the maximum between your siblings, 50, 30, 50. And if this is less than that maximum, you interchange them. So now 25 goes here. And now here you have 50. And you continue doing this. Okay, so this is 25. You compare 25 with 27. It's not the case, you stop. But if here, it's the case, 25 is less than 27. So now you have 27 here. And now 25 is here. Okay, so this is how you remove a value from the heap. And generally, when someone will ask you to remove a value from a heap, it's actually the first one. This is the idea of a heap, to give you the maximum value. Okay, and after that, you remove the value from the last node, you put it here, and after that, you compare the value with the maximum between the siblings, and you do an interchange if that maximum is greater than you, and you go downwards. Now, you may say that this is like the solution with the array. You see, I will search in the array the next maximum. Yes, but searching in an array of n elements, what's the complexity of that? So you have an array with n elements. How many comparisons do you need to do at maximum in order to get the max value?
n-1.
Okay, n or n-1, let's say n. But because this is a tree, it's a complete tree, what's the maximum number of comparisons that you need to do when you go with 25 downwards? You see, each time you do a decision, you split the remaining interval of values by 2.
And divided by 2.
No, it's a logarithm base 2 out of n.
Oh, okay.
Because you see, each time you take half of the remainder. It's like n divided by 2, n divided by 2 by 2, and this continue.
Okay.
Okay, so it's logarithm base 2 out of n. And that's why we are using a complete binary tree instead of an array. Because when you remove the max value from here and you try to replace it with the next maximum value from the remaining values, the complexity is logarithm base 2 out of n, which is a lot more smaller than n. Try to do logarithm base 2 out of 1 million. You will see you have a value with 2 digits. Okay. So you need to do a small amount of comparisons for high n values. Okay, now how do we implement this? So if you really try to implement this with the binary complete tree, I think we will not finish today or tomorrow, and we will have a lot of bugs. And there is this property, this very interesting property of a binary complete tree, which will help us a lot, and we can finish the solution in like, I don't know, 20 minutes. So if I will ask you to write the values from this binary complete tree, okay, or this one, the initial one, how do you read a binary complete tree? What do you think is the natural order? Let's see. I will clean the canvas. So let's draw it again. Okay, 2000. Okay, this was the root node, 50. Okay, 30. And now you get here 7 and 5. Now, what was the natural order of filling up this tree? From top to bottom and from left to right. So if I ask you to discard this binary complete tree in an array, how do you give me the values? So
from bottom to top?
No, from top to bottom.
Top to bottom, same.
Okay, and after that, so it's
50.
50.
Okay.
30.
30, no, 37 and 5.
Okay, so you keep the same relation. You traverse the tree in the same way we fill it up. So this is the array associated with this binary complete tree. Okay, so we have this, yes, this, thank you. It's what I draw. Okay, now, can we find a relation between the location of these values in this array and the relation of parent siblings in this binary complete tree? Let's see. If I draw the index here, this is the index in the array. Can we find a relation? For example, let's see. This is a value, 2000. It's the root node. Okay, and yes, we will reach to that formula. So let's see, its left side sibling or child is 50, index 1. The right side sibling is 30, index 2. Okay, so it's like 0, 1, 2. Now let's go for 50. 50 has an index 1. Okay, so I will draw the index here, 1. And let's do this one. Okay, and its left side child is 7, which is, it has the index 3 inside the array, and the right side sibling is 4. So it's 1, 3, 4, and here we had 0, 1, and 2. Okay, I think I can, let's say, distinguish a relation. So this is 1, and the left side is 3, and the right side is 4. Okay, and this one is 0, and 1, and 2. Let's draw some new values here. For example, 15. Okay, and maybe 20. Okay, and I will fill up the array. So it's 15 and 20 here. Okay, and their index will continue. It's like 5 and 6. So here we have 5 and 6. So it's 1, 3, 4, 2, 5, 6. So I think this is 1 multiplied by 2 plus 1. And this is 1 plus 1 multiplied by 2. You see, let's check for this one. So this is 2 multiplied by 2, which is 4 plus 1, it's 5. And the right side sibling is 2 plus 1 multiplied by 2. So 2 plus 1 is 3, multiplied by 2 is 6. So what's the relation between the index of a node, let's say I, and its right and left side sibling? So the right one, okay, is what? I multiply by 2 plus 1, and the left side is actually I plus 1, everything multiplied by 2. And this is always true for a binary complete tree. So if we can simulate a binary complete tree using an array, don't you think it's much more easier to use the array? Because you see, by having this relation between the two siblings, we can easily find where the left child of 50 is here and the right child is at any moment for any values here. And because of this property, that's why a heap is actually a binary complete tree, but is always implemented using an array because it's faster. Okay, you don't need to use pointers, it's just an array. a simple array, and we always use this relation between the position of a node and its child nodes, the left and the right side one. And if we can determine based on the node index where the child nodes are, I think we can do a reverse on these relations in order to say, hey, what's your parent node? So if you are 15 or 5, what's your parent node? And you see it's actually a division by 2. And we take the integer part of that. Okay, so this is what a heap is, and these are the general rules of a heap, and this is how we implement it. Okay, now let's try to do, I only need 10 minutes to do the, let's say, the insert, and maybe we have time to finish. Okay, if you have any questions, now this is actually the important part of a heap to understand the story, because otherwise the implementation is quite easy. So it's just an array, we play with an array, and that's it.
Deci la funcțiile respective e I ori 2 plus 1 pentru dreapta și la stânga I plus, nu, I ori 1 plus 2.
Stai să văd, să nu fie greșit. So the right side is, yeah, I think they are actually in reverse. So I multiply by 2 is, yeah, so this is the left, which means, no, it's right as you look at the screen. So this is the right child, this is the left one. So 1 multiplied by 2, yeah, so they were actually, let's fix it. Okay, so let's say this is the left and this is the right. Yeah, so thank you for the question. Initially it was written then in reverse. So this is the left side, this is the right side child. So if you know if you know the index of this value, in the array, the left side child is I multiplied by 2 plus 1, and the right side is I plus 1, everything multiplied by 2. Okay? Okay. Right or left. Okay. Other questions, if you have other questions. Okay, so let's switch to Visual Studio. So we have the Meteo alert. So let's define the structure. So struct, let's say heap, alert, alerts heap. Alerts heap. Okay. And as I said, we implement it, we design it, okay, we design it or we think at this structure as a complete binary tree, but it's actually the implementation is an array. So let's define an array here of Meteo alerts. So Meteo alerts, let's say alerts, okay. Now we can go for a dynamic heap, but we need to define its size. So let's suppose at some point it's like we think as a hash table, at some point we need to resize it because maybe we fill this up. So let's go for a dynamic approach, alerts. So what we need to know about this one is the capacity. So what's the maximum number of elements? So number of maximum elements that we can store. Remember, adding a new value into array, into a dynamic array, it's a very costly operation. You need to reallocate the array, copy all the values. So let's try to minimize this impact by always creating an array with a fixed size. And when we reach that size, we extend it, okay? We double the size. So in order to reduce the number of insertions, because otherwise we lose time there. Okay.
Mai bine decât să îl dublăm, mai bine îl facem cu jumătate din size, cum e radius-ul din Java. Că e mai...
Okay, so if you have half of the size, when you reach half of the size, you need to resize it, right?
Da.
So what do you do then? You double the size?
Nu, eu crești capacitatea cu jumătate din size-ul actual. Gen dacă...
Okay, that's a good idea. Now, I will always go for doubling the size because this will grow exponentially. So if you have a lot of insertions, I want to limit the number of resizes. So by using double, that will grow exponentially.
Oh.
You know, that's why I choose doubling, but I can go for your idea. It's okay. So let's say we add half of the capacity, right?
Yes.
Okay, great. So this is the capacity, the number of maximum elements. So here we have the number of actual elements. Okay, number of actual elements. So the idea is that we need to keep number less than capacity. If we reach the capacity, we need to resize it. Okay, so this is how many elements we have against what we can store here. Okay, so okay, this is the alerts heap. Let's define main. Just to be able to...
Și mai am o întrebare. La resize, de ce nu facem cu realloc? Că trebuie doar să realocăm...
Okay, we can use realloc. I don't have an issue with that. Okay? So we can use realloc. Let's use realloc. Okay. I think the correct answer is that when I went through this as a student, we never, and I think we were not allowed to use realloc. So yeah, this was the effect. I'm still not using realloc. So yeah. Let's create a function that creates the alerts heap, init heap. So here, what do we need? Initial size. Initial size. Okay. So here we want to do what? Alerts heap. And now let's initialize the capacity equals with initial size. And also heap number of elements 0. Let's be sure it's 0. We can initialize it also here. Okay, and now alerts equals with meteo alerts asterisk malloc of what? Of initial size multiply with size of meteo alert.
What's the difference between malloc and calloc?
The addition.
Calloc.
Yes. I saw a function the other day, calloc, but I did not understand the difference between them.
Yes, you don't put the asterisk. You just
Yeah, malloc.
Initial size and size of meteo as parameter.
Yeah, let's see. Calloc in C. Okay. Initialize the data. That's
okay.
Yeah. So I'm here in the official or one of the so allocates a block of memory of an array of num elements. So it has the size. Okay. Each of them size by long and all the bits to 0.
Oh, okay, I understand.
Okay. So you see here it's initializing I elements of size of int, and they are all 0. All the bits. Okay. And generally, when you have an integer with all the bits 0, you have the integer 0, but it's all the bits. Okay.
Oh, okay.
All the bits. Okay. So yeah, I think that will be even greater in Visual Studio, where let's say some compiler versions will initialize with 0xCCC. So in that case, I think it's even more recommended to do calloc, because you will get all the values 0. Okay. Yeah, because null is 0 in C. So that's why you get null, because it's 0. So yeah, I should recommend you to use calloc. It's safer. Okay. Now, what are the values for all these initial size meteo alerts or meteo alert? So you have now initial size values of meteor alerts. Here you have 0xCCC, for example, or 0 if you go with calog for all those bytes, and the priority will be what? So once again, always take care of this. You either initialize them here, 0 and here, yeah, you get the value. But when you create the array of meteor alerts, they are not initialized by this property here. This works only when you do a value, meteor alert, let's say alert. You get a 0 there, but not here. Okay, so always init your values, because otherwise you may get 0xCCC, you may get any value there which is not 0. So if you want to get 0 there, you need to be sure. So for int I at 0, I less than initial size, I plus plus, heap alerts at index I equals, and now you want to initialize them with 0. For example, let's say you do a meteor alert, initial alert, or empty alert. Let's say empty alert. Okay, now you define it, and now you can initialize it. Now I think another function was even greater here. This is the way we did all our previous examples. So let's do the function here, init alert. Okay, and here we have a const char asterisk message and int priority. Okay, so here I will do a meteor alert, and here I will do a string copy, because we don't need to allocate space, into alert message. Okay, now I have an issue here with string copy because I didn't include the string.h, and I will do that. But let's finish this initialization. Priority equals priority, and let's not forget to return alert. Okay, so I need to include a string.h for this value here, for this function here, like this. So include string.h. Okay, so just add this library here. Okay, now we can init an alert. So I will use this function here. Okay, meteor alerts empty alert equals with init alert of empty string and priority 0 or -1. So if you consider that you will never get alerts with a priority less than 0, you can init them with either 0 or -1 if the priority will always be positive. Okay, so choose a value that will not mess up when you try to decide which is the maximum alert. Okay, you need to value to be a neutral value that will help you get the maximum for new alerts. Okay, so here I have an empty alert, and here I will initialize all my initial alerts in this heap in order to be sure that, let's say, they are not initialized, they are not valid messages. Now, once again, I remind you, and last seminar we did this, equal works because we don't have pointers in message alert, meteor alerts. Because otherwise, if you have a pointer there, this will do a shallow copy, and you don't want to do that. Okay, so you need to create your own function for copying a meteor alert if you have a pointer there. So each time I emphasize this. And in this case, we don't have a dynamic field there. We don't need to create space. So the copy paste will work, and that works also for static arrays. Okay, so here I created the initial heap and let's return it. Return heap. Okay, so we have it. And now let's do the two functions that will help us get the right and left sibling. Okay, so this is our some utility functions. Int get right child index, int index. So based on our formula, this is actually return. And for the right one was index plus 1, everything multiplied by 2. And a similar function for int get left child index, int index. And here you have return index multiplied by 2 plus 1. Okay, so now if you know the index of a node in the array, you can easily determine its siblings. Okay, and for its parent, get parent index, index, int index. You will see that this is actually this formula. It's a integer-based division. So if I go here, where is the whiteboard? Here. Okay. So for example, for 3, if you divide this by 2, this is 1 and something. But if you take the integer part is 1. And here, if you divide this by 2, it's 4 divided by 2 is 2 and minus 1. So let's see here. 5 divided by 2, it's 2 point something. So the integer part is okay. And here it's 6 divided by 2 is 3 minus 1. And we need a general formula. So the general formula that works for either left or side is actually this one. If you do a division by 1 here, subtraction by 1, and after that you divide by 2, you will always get the integer part, which is the index of your parent. And it doesn't matter if you are the left or the right sibling. So let's see. 5 minus 1 is 4, divided by 2 is 2. 6 minus 1 is 5, divided by 2, it's 2 point something. And you always get the integer part. So you see it's always 2. So 3 minus 1 is 2, divided by 2, it's 1. 4 minus 1, it's 3, divided by 2, it's 1 point something, and you take the integer part. So this is always return, just to be sure. But if the operands are integer type, the division is integer based. So return integer of index minus 1 divided by 2. Okay.
You can see visual studio anymore.
Yeah. Sorry for that. And thank you for notifying me. Sometimes I forget to switch the share screen option. Okay, so this is always the parent index. You subtract 1 and you do an integer-based division. Okay, so just to be sure. So we know how to determine the parent and the child. Okay, so what do we need to do? To insert something in the heap. Okay, so void insert. What do we need in order to insert? The heap. So this is the alerts heap. Okay, let's think for a moment. When you insert something in a heap, what is changing here?
Number.
The number. So a variable is changed inside the structure. And in order to preserve the change, we need to pass the structure because some of the variables, the attributes is, yeah, exactly, are changing. We need to pass it by pointer. Okay, so that's why always ask yourself this. Hey, it's any of the attributes is going to change? If yes, you need to pass it by pointer. And here we need what? Meteo alerts.
Can't we use also the ampersand for the heap?
No, this is a course level decision. We are not allowed to use the C++ reference. Yeah, we are stuck to C.
Oh, okay.
Yeah. Sorry for that.
I used in homework the ampersand, but
okay, I will look to the other side. Okay, but try not to do that for the for the exam or for the test. Okay. So yeah, this is something we already discussed, and this is the decision at course level. Everybody's doing this. Okay. Yeah. So yeah, try not to use reference, please, because we already established that because otherwise why we are not using new, and the story can go on. So that's why we use C functions. So we are in C++, but we program in C. Okay. Yeah, the pointer is specific to C, but the pointer is also specific to C++. The actual correct affirmation is that the reference or the ampersand is specific to C++. Okay, only to C++, but the pointer, the asterisk, is from C and also in C++. Okay, it's specific to C and C++. Okay, but the ampersand is only to C++. They introduce it in C++. Okay, so when we insert something, the first thing that we need to do is to check if we have available spaces. Check for available space. Okay, how do we know that? So what we want to do is to see if the heap number of elements, okay, by pointer, because we get it by pointer, if heap number of elements is, let's say, less than or equals with heap capacity -1, it's obviously or it's equal with capacity, actually, we don't have any spare locations, because remember, we need to add the new element on the next available location, and in this case you don't have it. You will get on index out of bounds, so we are exceeding the array limit. So in order to do this, we need to, what your colleague was already telling us, to resize it. So let's resize the heap. So this is a function for resizing it. Resize heap. And here you need what? The alerts heap. And once again, because we resize it, everything will change. The pointer to the array values will change. We need to pass it by its pointer. And we will use your colleague's suggestion by increasing the size with half of the available capacity. Okay, so that's why I don't need another value, because I know it's a standard. We choose a standard algorithm. So in this case, what do we need to do? We need to do a new array, the new array. Okay, so meteo alerts new array equals with meteo alerts asterisk malloc of what? Of heap capacity plus heap capacity. So here you either double the size or capacity divided by 2. It doesn't matter. You just need to resize it. You can choose an algorithm. Okay, and this will be the new size. And here will be size of meteo alerts. Okay, so now we resize it. Too many arguments in function call. Let's see. Capacity plus, okay. Where are the too many? Size of, let's save this one. What?
You have a comma after the heap capacity.
Heap capacity divided by 2. Where is that?
It's for C-alloc, not for malloc.
You have a comma before size of.
Multiply.
It's times.
Yeah. Sorry.
That's okay. It's okay.
Yeah. Thank you. Let's see on chat. Yeah, it should be multiply. Yeah. Now I'm back on the tracks. Okay. It's multiply size of. Now let's be sure that we are not doing a trivial mistake regarding the order of operations. Okay. We want to do the division and the addition before doing the multiplication. Okay, so this is a trivial mistake. It's easy to do it if you are not paying attention. Okay, because otherwise you will do the division and the multiplication before that. Okay, so it's capacity plus that one divided by 2 multiplied with size of. Okay, and now we need to copy the existing values from the heap in the new array for int I at 0, I less than heap dot number of elements or capacity. We know they are equal in this case, but maybe sometimes we need to do a resize when we don't reach this condition. So let's choose number I plus plus. Okay, and here will be new array at index I equals with heap alerts at index I. Once again, this works because, okay, we don't have pointers. You got the idea. Okay, so always watch out for this kind of stuff because otherwise you will do shallow copies. Okay, so here now we copied everything into the new array. We can discard the old one to avoid the memory leak. We were talking about this. So delete heap.
Free, you mean?
Yeah,
we have malloc.
yeah. Okay, you see, you switch me to C++, and now my subconscious is there. I need to get it out and move it to C. So free heap alerts. Okay, let's change the pointer here to the new array equals new array, and also let's change the capacity to the new value. So this equals with this value here. For that, I think another variable was more appropriate. And now let's return the, no return, it's a void. Okay, so in this way we can resize the heap. And how do you use this function here in this function? So always watch out for pointers to pointers. Okay, so here we need to resize it. So this will be like this, resize heap, but don't try to write this. Fortunately, you have a compiler, which is your only friend. So if you do it, let's say automatically, every time you need to pass the address of a variable and you write the address of heap, fortunately, you have a friend, which is your compiler. And you see, it's giving you this compiler error. It's saying, hey, here, you said you will give me a pointer to a heap, and now you are giving me a pointer to a heap. You see, argument of type alerts heap to asterisk is incompatible with parameter of type alerts heap. Why? Because here you just need to pass the address of the heap structure. And you already got it because you get the address of that structure. So here you need to pass it along. And fortunately here the compiler will give you that compiler error. And you should realize that you already have the pointer. You don't need to get the address of the pointer because if that will be allowed, you will pass a wrong value, a wrong address. It's different stuff. Okay, so in this case, because you already get the pointer, you just pass it and resize. We'll use that pointer to resize your heap. Okay, so this will be done only if you need to resize. Other than that, with the resize or not, what means to add a new alert here in the heap. So based on the algorithm, on the previous algorithm, the new value will always go in a binary complete tree on the only location where it should go, which is the next free available location in the binary complete tree, okay, which is, let's say, either this one if it's free or either this one in this case of this heap. But for the array, the next value, the value here, this location is always, question mark, is always this one here. The next available location in your array. Okay, so this correspondence once again is helping us to use more efficiently the array representation over going for a tree with pointers and so on, because you will always know that this location will be the equivalent of this one or this one or this one. Okay, so for us, adding the new value in the heap in the last location, let's say, it's very simple in this array because we know where that is. So add the new value in the heap, which means we know we have the space. Heap alerts at index heap, and we are in C. So we know that the index is from 0 to number -1. So the last location, or the next free location after the last one is actually n. Okay, so if heap number equals alert. Once again, this works because, okay, so this works because of that. Once again, I will write this here. Okay, now this is not sufficient. We want to be sure that if this is the message with the highest priority, it will get to the top. So how do we do that? We need to go upwards, okay, by checking the last node value and comparing it to its parent. And if it's less than, greater than that, we do an interchange and we continue until we reach the root node. And it's easy to determine when we reach the root node because the index will be 0. You are here, it's the first location in the array. Or we stop when the current node has a value less than the parent one. So these are our two exit conditions. So we can do this in different ways. Now, generally, I will always go for something in steps. So let's say this is an infinite loop. I want to decide when I will exit myself. We can write this in a different way, but I will always do this. If, how do we compare this with the parent? We have a function, parent index, that will give us this value. So parent index. Now here I will define another value, which is the current index. Okay, the current node index. Okay, and in this case, this is what? Heap number. Okay, now where after we added the new value in the heap, let's not forget this. Let's not leave this for later and forget about it. So let's increase the number of elements. Plus equals 1. But if you do this here, then the current node index is -1. Okay, because we just increase it. Okay, so we know we are here. And each time we want to get the parent index value. Parent, let's say node index. So it's get parent index of current node index. Okay, so we got that. So what do we do here? We compare them. Now we know that if the current index becomes 0, it means you reach the top. You don't need to check anything. You are on the top of the world. You need to exit. So if current node index equals 0, break. Okay, so we exit the while true, the infinite loop. Okay, so this is our one of the exit conditions. Now, if int parent node index, so we got the parent, let's compare the values. Compare the values. So if heap alerts at current node index dot priority, this is what we compare, the priority, and this is the current node. So we are interested in the scenario where this priority is greater. Now, if they are equal, it doesn't matter. The parent is already there with a higher value, so you don't need to do the interchange. You can just leave the nodes as they are. But if this is greater, then heap alerts parent node index dot priority, then interchange them. Okay, so in order to interchange them, we have the classic algorithm, which generally means create a temporary meteo alerts, let's say temp. This is equals with one of them. It doesn't matter. Heap alerts. Yeah, current node. Okay, now heap alerts current node index equals the parent value. Parent node index. Okay, now the heap alerts parent node index becomes the temp. Okay, and after you interchange them, you need also to change the current node index. So the current node index is now the parent node index. Okay, so this will interchange them. It will interchange the new inserted node with its parent because the new node has a priority greater than its parent. Okay, and now this will go back here. Now you check to see if you reach the top. If yes, you exit. If no, you get a new parent node index and you compare them again. Okay, so at some point you either exit by this or by this. Else break. Okay, so this will exit the infinite loop by these two exit conditions. Reach the top, or you find the location where your parent has a value greater than you or equal, so that will not justify an interchange. Okay, and that's it. So this is the insert in a heap. Okay, in order to be sure that this works, and after that we stop. I already exceeded the seminar time. Sorry for that. Maybe you have other activities. I hope you don't. But if you have, yeah, sorry. I will give you the record of this seminar so you can leave and attend other activities. I will just continue in order to finish the insertion, in order to be sure that this works. So in order to test this, now generally this doesn't make any sense to print a heap, but in our case, let's print it. So I have a method here, the print meteo alert method, meteo alerts alert. Okay, so printf, and here I will have something like the message. Let's put the priority, and after that the message. So it's alert priority, and after that alert alert. Okay, so this will print and the backslash n here. Okay, and now let's do a method to print the heap. Print heap. Now this is not a normal function for a heap. Generally you don't want to see what's there. You just want the maximum value from that heap. But in this way we can check if the insertion is okay. So print heap, and here I need the alerts heap. So generally this means only one thing. Printf backslash n heap values. Okay, and for int I at index 0, I less than heap dot number of elements, I plus plus. We just do a print meteo alert of heap dot alerts at index I. Okay, so this is a very simple method to check if everything is okay. So let's test this. I will create a alert heap. Okay, equals init heap. So let's start with an initial size of 100 values. Okay. And now let's insert a heap. Okay. So message meteo alert. Meteo alert, let's say alert 1 equals with, we need to follow the structure. Oh, we have the init, sorry. Init alert of, and I think we can skip the alerts. We can insert by calling init alert. So let's say sunny weather, priority, I don't know, 5. Okay. And after that, we insert this heap, insert into heap the address of the heap alert 1. Alert 1. Okay. And after that, I will duplicate this line. So here I will init alert and let's pass some values. Rain. So after this one, let's say this has a priority of 25. Okay, let's duplicate the line again. Heavy rain, 50. And after that, another sunny weather of windy, let's say wind, a windy day, and let's say 25. And after that, the last one, strong wind, wind 200. So if I print the heap now, print heap, if everything is okay, we should see, and this is the first check, we should see that the first alert message, meteo alert, is the one with 200. Okay, this is the idea, to see it to be the first one. So Control F5. I have a compiler error, and yeah, I expected this. Maybe you don't have this problem, so I need to disable the secure life cycle. So define CRT secure no warnings. Okay, so let's do another test, build, rebuild. Okay, in my case, everything looks okay from this perspective. Now let's see if this actually works. Okay, so Control F5 again. And let me share you my console. So I have 200 strong wind, heavy rain, sunny weather, and windy. Now, if I will simulate this on a whiteboard, in order to be sure that the insertion is really working, so you have 250, 25, 5, 25. Let's switch back to Visual Studio. I will close the console, and I will open the whiteboard again, full screen.
I have a question now.
Yeah.
We use the ampersand here in the insert, and
yeah,
if we used it, isn't it the same if we used it in the insert method?
So this is the insert method here.
Yes.
Okay. So your question is,
we used in the main the ampersand anyways, so
yeah, because here based on the insert definition, here we are saying I'm not giving you an heap article, I'm giving you its address. So in main, yeah,
sorry, it means it's not C if we use, I think that's what he means. We use reference anyway.
Yes.
Because you, Professor, you earlier said that we shouldn't use ampersand because it's a C++ specific thing.
Yeah, but this is not the ampersand. So the C++ ampersand is here.
Okay.
Is a reference in the function.
Exactly. It's a it's a wrapper or an alternative to the pointer, but it's a data type. So the ampersand, the C++ ampersand is a data type. It's like a new data type, but it's not actually a new data type. Change value. You see, in C, if you want to give me a variable in order to change it here, like VB, let's say VB equals 90. So you send me a value with any value, a variable with any value, and I change it to 90. In C++, they said, hey, why to do that change value C++? Instead of writing asterisk, and this will force you to use the asterisk again and again, let the compiler do that for you. So here is VB90. But this generally, this from here translates to this, okay? So the C++ reference, which we can't use, is this one, the reference as a type, okay?
Okay, I got it.
But for pointers, if you say, hey, this function receives a pointer, an address of a variable, how do you get the address of a variable? This is the, let's say, the address operator from C.
Okay.
Yeah? Because the C++ reference, you see it only here. If you call change value CPP, you don't write this again.
Yeah.
Okay? Okay. So now, in order to end, let's see if the values from the console are, let's say, in the correct order. So if I open the whiteboard again and follow what this insertion is doing, okay. So whiteboard, let's here. So if I clean the whiteboard again, clean canvas. So what was the first value that we got? Can you, in order not to switch to Visual Studio? In the heap, what was the first value that we inserted in the heap?
5.
5. So we have an empty heap. So 5 is actually the root node. Now the second one, after 5, we get
25.
25. So when you get 25 here, the algorithm will interchange them. So this is initially, but this will translate with 25 here. Remember, it's comparing the parent, and now you get 5 here. Okay. So the next one,
50.
50. So 50 normally goes here. And now we compare, is 15 greater than 25? 50. Oh, sorry, 50. Okay, so 50. Now, is 50 greater than 25? Yes, so this translates to 50 here. Okay, 5 and 25 because of the interchange. Okay, this is the while in the insert. What other values we got after 50?
25.
25 again. Now, the second 25 goes here. Once again, you check against its parent. So this leads to this 50, 25 because of the interchange and 5. Now we once again compare 25 against its parent. It's less than that. So this was the second exit condition. So we stop. Okay. And after that, we got what?
200.
200. So 200 goes here. This is the next available location in this complete binary tree. And now we do the comparisons. So 200 is greater than 25. So this leads to this intermediary image, 200 here and 5 and here 25. Okay, and the while continues because we need to do another interchange. So 50, okay, 5 and 25. Okay, so this is the final heap version. Now, if this is translated to an array, this is actually 200, 50, 25, and 5. So this should be the correct order in our example. Let's run it.
At 25.
I forgot what?
At 25. Yeah, there.
Oh, okay. Sorry for that. So yeah, the 25 goes here. Okay, but this is still here. So here we got another 25. Thank you for that. I was I was going to see this when we compare with the console that I'm missing a value, but thank you.
Yeah.
So it's 250, 25, 5, 25. So if I run the example again, Control F5, I will switch. Okay. So new share. Okay. We have what? 250, 25, 5, 25. And I think this is actually what we draw. 250, 25, 5, 25. Okay. So this is how we check if everything was okay. Okay. And at this moment, we know that our insertion works. Now, for deletion, for deleting a value, now where is the maximum? So let's say Meteor alerts, and I will open this function, but you need to finish yourself. Meteor alerts get alert. Okay. Once again, the heap is changing. Heap alerts, you need to pass it by pointer because you will remove one element. You don't ask from where to get the alert. Is the first one. This is the result. Is the first one. Heap alerts, sorry, alerts at index 0. Now, the only thing that you need to check here, if you have a value there on the first location. Okay, so you need to check if you have a value there, but in the end you need to return this one because you have the assurance that is the first one. This is the heap definition. Now what you need to do here between these two locations is to replace the first value with the last one and do the comparisons downwards. Okay, like we explained in the beginning. Okay, so you need to do this in order to fill up the first location because you just remove one element. And in the end, the heap number of elements is decreased by 1. And the next maximum will be on the first location again. So if you call get alert again, you will get the next one and the next one in line. Okay, the next with the maximum value. Okay, and in order to do that, you need to use the two functions. You need a function to determine which is the maximum between the two siblings. You can determine where the two siblings are in the array, and you replace them if that's the case. Once again, you compare them. And watch out for not exceeding the array boundaries. Okay, so this is the heap discussion. So the data structure solves only one problem, which means if you need a data structure that will deliver you as fast as possible the value with the maximum priority, okay, the solution is the heap. Okay, this is the only purpose of this data structure. It's not for searching, it's not for storing, it's not a dictionary. It's just a data structure that delivers as fast as possible the maximum priority value or article or whatever. So you need to have a priority-based logic or a cost or whatever.